All right, so let's talk about 3.1. Okay, so 3.1 is about, sorry, there we go. So 3.1 is about implicit differentiation, and so the idea is that, it's not always practical to explicitly express y as a function of x. So, and here are a couple of examples, right? So if you have something like x cubed plus y cubed equals 3x squared, it's possible to solve this equation for y. You don't get just a single function out of this. I think you end up with 3 separate kind of solutions, and they're very, very messy to express in terms of y. So, so we don't necessarily want to do that. And then another example would be sine of xy equals y. Now this thing is not even possible to solve for y. Okay, you can't solve this thing for y. I mean, you might think, well, it looks like y equals sine of xy, right? But I mean, you still have a y in here. So it's not possible to express this function just in terms of y itself. So the good news is that we can still calculate derivatives. We can still calculate dy dx for equations like these using implicit differentiation. And the idea is that we assume that y is a function of x. So whenever we're differentiating functions in y, we will require the use of the chain rule to do that. So in particular, let's say that you wanted to calculate the derivative of with respect to x of y squared. And so we're assuming that y is a function of x, right? So we calculate the derivative of y with respect to x, right? So what would that be? Well, first of all, we differentiate y squared the way that you think you would, right? So you would move the 2 down and say 2 minus 1 is 1, and so the derivative of y squared is 2y. But then we use the chain rule because y is actually a function of x. So we do 2y times whatever that is, right? Whatever dy dx is, and we may not know it off the top of our head, right? So we may not know what y is as a function of x, but whatever it is, right? We multiply by dy dx. And so that's how we differentiate. This is called implicit differentiation. Basically, the moral of the story is whenever you're differentiating with respect to x, and you're differentiating some other variable that you're assuming can be expressed in terms of x, then you need to apply the chain rule to do that. Okay, so I'm going to give you a couple examples of this. So let's find dy dx for xy equals 1, and we're going to do this in 2 ways. So the first way is we're going to use implicit differentiation. Okay, so I'll show you that way. And then the second way that I want to do it is by solving for y first. So we'll solve for y first, and then we'll do some kind of like normal differentiation, I guess, whatever that means, right? So, so here we go. So using implicit differentiation, here's how this would work. We've got this equation that says xy equals 1. So if we want to differentiate it, right? So we're starting with, xy equals 1, and we want to differentiate. So we're going to take d dx, right, of both sides of this equation. Okay. Now the derivative of a constant is just 0, so the right hand side is going to be 0. On the left hand side, though, we have a product of x times y, and so we have to use the product rule, right? So this is going to be the derivative of the first times the second plus the first times the derivative of the second. Okay, so that's the product rule, and then that's going to equal 0. Okay, so let's see, derivative of x is just 1. derivative of y is also 1, but we have to use the chain rule, right? So it's 1 times whatever the derivative of this function in x is, right? Which we usually call dy dx, right? And there you go. So we've found dy dx. We just need to solve for it now. So we have y plus x dy dx equals 0. That means that x dy dx equals negative y, which means that dy dx equals negative y over x. Now, if you wanted to get this just in terms of y, of course, you could solve the original equation for y, which is what we're going to do in part B anyway. But just for the sake of argument on this one, we could say, well, xy equals 1 implies that y equals 1 over x. And now you can plug this in for y there and get negative 1 over x, which is negative 1 over x squared. Okay. So that's the first way to do it. The other way to do it is to just solve for y first, right? So xy equals 1 implies... By the way, this is something that I see a lot on your quizzes. You seem to not know the difference between an equal sign and an implies sign. So let's just take a moment to appreciate the difference for those of you who are going to watch this video. Because the other thing that I've noticed is that a lot of you don't watch these videos. So I might be preaching to the choir here, but you wouldn't say that one expression implies another. Like saying, 2 plus 3 implies... I don't even know what you would say. You wouldn't say 2 plus 3 implies 3 plus 7 or something. I mean, the correct notation is to use an equal sign. So if you have two expressions and you want to say that they're the same, then you say that they are equal to one another. Okay? The implies sign is something else. It's like the implies symbol means that if this is true, then the thing that follows is also true. Okay? And so you would use an implies symbol whenever you have a complete sentence that implies another complete sentence, not just a sentence fragment implying another sentence fragment, right? Anyway, so that's just kind of a nitpicky thing, but xy equals 1 implies that y equals 1 over x. Okay? And then we can find dy dx pretty easily. Oh, by the way, this is x to the negative 1 power. See how I'm using equal signs? Because these are all equal to one another. Okay? Anyway, I'm not using implies signs. What I could say, so just for the sake of argument, if we have xy equals 1 implies y equals 1 over x, instead of saying y equals 1 over x equals x to the negative 1, I could have said y equals 1 over x, which implies that y equals x to the negative 1. Right? But you see how each of the things in here are complete thoughts. Okay? Anyway, but so dy dx is going to be negative x to the negative 2, which is negative 1 over x squared, which is just exactly what we got the first way we did it. Now you might be thinking, well, but part A looks like so much more work than part B. Why would we ever do implicit differentiation? Well, but it's because this particular equation was easy to solve for y, but like the examples that I showed you a second ago, not all equations are solvable for y, and even some of the ones that are solvable for y are not easy to solve for y, and so we use implicit differentiation. So let me give you another example. And this would be one where we wouldn't want to do it using the method of part B, right? We're going to want to do this using implicit differentiation. So let's use implicit differentiation to find dy dx. And let's do this for 5y squared plus sine y equals x squared. Okay, So here we go. Anytime you differentiate something with a y in it, you need to have a dy. You need to use the chain rule. So you need to multiply by a dy dx. Okay. So looking at this first term, if I differentiate this, it's going to be 2 times 5y to the 2 minus 1. So in other words, 10y to the first power, right? This is going to be 10y to the first power. But because I differentiated a term involving a y, I've got to have a dy dx, right? I've got to use the chain rule. So times dy dx. Plus sine of y. Well, the derivative of sine is cosine, so this would be cosine y. Again, got to use the chain rule, dy dx. And on the right-hand side, I'm going to take the derivative. Derivative of x squared is 2x. This time I don't need to have a dy dx because I'm differentiating with respect to x. And so there's no need for a chain rule here. Okay? So I'm just going to have 2x on the right-hand side. I need to be able to solve for dy dx. So what I'm going to do is factor out the dy dx from the left-hand side. 10y plus cosine y. And then I'll finish solving for dy dx by dividing through by 10y cosine y now. I'm going to say dy dx equals 2x divided by 10y plus cosine y. And there's your final answer. Okay. So that's that one. Let me give you another one. So we'll do x cubed y squared minus 5x squared y plus x equals 1. Okay. So using implicit differentiation here. Okay, here we've got a product, so we're going to use product rule. We'll have the derivative of the first times the second. Okay, no need for a dy dx there because I didn't differentiate this part of the product, right? I didn't differentiate the part of the product that has a y in it. So no need for a dy dx. So it's the derivative of the first times the second plus the first times the derivative of the second. Now that's going to be 2y, and this time I do need a dy dx. Okay. So this is just for x cubed y squared. Okay, that's the derivative of x cubed y squared. Now I need to subtract off the derivative of 5x squared y. Again, I'm going to use product rule. So this is going to be 10x, so derivative of the first times the second, plus the first. By the way, I should have this in parentheses. Plus the first times the derivative of the second. So derivative of y is just 1, but again chain rule, times dy dx. Okay, so this whole thing is just the derivative of 5x squared y. And then I have to add the derivative of x. Well, derivative of x is just 1. And then on the right-hand side, I need to differentiate a constant. Well, the derivative of 1 is just 0, right? The derivative of a constant is 0. Okay, now my goal is to solve for dy dx. So let's see if we can do it. I'm just going to clean things up here. I've got 3x squared y squared plus x, maybe I'll call it 2x squared y dy dx. Minus 10xy minus 5x squared dy dx plus 1 equals 0. Okay. So now the trick is, if I want to solve for dy dx, the trick is I'm going to move all of the terms that don't have a dy dx attached to them to the right hand side of the equation. and I'm going to leave all of the terms that do have a dy dx attached to them on the left-hand side of the equation. That way I'll be able to factor out the dy dx. Okay, so I have 2x squared y dy dx minus 5x squared dy dx equals, and then I'm going to move this term over, so it's going to be a negative 3x squared y squared. I'm going to move this term over, so it's going to be a plus 10xy. And I'm going to move this term over, so it's going to be minus 1. Now I can factor out the dy dx. And then I'm going to divide through by the leftovers, so that dy dx is equal to negative 3x squared y squared plus 10xy minus 1 over 2x squared y minus 5x squared. And that's that one. It's possible you could factor some of these, I guess. I'm not going to really try. Well, maybe I should. I don't know. The denominator, definitely I can take out an x squared. The numerator, can we factor that thing? If we can, maybe I'll take out the negative, make things a little bit easier on me. So it would be negative. We'd have to have a 3xy and an xy in order to get an x squared y squared and to get a 10xy in the middle. I wonder if we can get the because to get a plus 1 it has to be a 1 and a 1, right? That's going to be 3 and 1. I don't think it factors. I don't think the numerator factors. Anyway, so that's as far as that one's going to go. So that's that. Let me give you another example. On this one, we're going to use implicit differentiation to find d squared y over dx squared. So we want to find the second derivative this time. If 4x squared minus 2y squared equals 9. Okay, so let's do it. Okay, so first of all, let's differentiate, right? So differentiating the first term, I'm going to have 4 times 2 is 8, so I'm going to have 8x to the first power. And then differentiating the second term, I'm going to have 4y to the first power, chain rule, right, times dy dx. And then on the right-hand side, derivative of 9 is 0. Okay? So let's solve for dy dx. We'll have negative 4y times dy dx equals negative 8x. And then I can divide through by negative 4y and get dy dx equals negative 8 divided by negative 4 is 2, right? So I'm going to have 2x over y. So that's not bad. That's not nearly as scary as what we started with, I think. But we're not quite done because we need to find the second derivative. So let's find the second derivative now. Okay, so we're going to say d squared y over dx squared is going to be the derivative of this thing, which is a quotient rule. This is going to require a quotient rule. Or maybe instead of doing quotient rule, we can do 2xy to the negative 1 like that and do product rule instead. Whatever you prefer. You'll get the same answer, hopefully. You should get the same answer either way. So let's see. I'm going to think of it like product rule with this thing. So I'm going to do, I'm thinking of 2x as my first function, and then y to the negative 1 is my second function. So it's going to be derivative of the first times the second plus the first times the derivative of the second. So derivative of the second is going to be negative y to the negative 2 times dy dx because of the chain rule. Okay? Let's see if we can clean this up. d squared y over dx squared. I'm going to call it 2 over y plus, or minus, because of that negative sign, we call it minus, let's call it 2x over y squared times dy dx. Now what do we do with this times dy dx thing? Well, up here we solved for dy dx. We said dy dx is 2x over y. So really, d squared y over dx squared is 2 over y minus 2x over y squared times dy dx. But dy dx is just 2x over y. Okay, so that would be 2 over y minus 4x squared over y cubed. And that would be your final answer. You could, get common denominators and stuff and combine this if you want. I mean, this would be an acceptable answer for me, but maybe the back of the book has something slightly different and you're like, why, So you could get a common denominator, right? Multiply by y squared here. And then you've got 2y squared minus 4x squared over y cubed, right? And then maybe they do some factoring or some other stuff. I mean, I don't know. But you have to be pretty good at algebra sometimes to make your answer match the back of the book. But anyway, that's the idea on that one. Okay, let me give you a couple more examples. Okay, so let's find the slopes of the tangent lines to the curve y squared minus x plus 1 equals 0 at the points to negative 1 and to positive 1. Okay? So at these 2 points you're going to have, well, maybe they're the same slope for all I know. I don't know. But we're going to calculate the derivative first of all, and then evaluate that derivative at these 2 points. So let's get to it. So differentiating this equation implicitly, we would get 2y times dy dx, right? That's the derivative of that first term, minus 1, right? Derivative of x is just 1, plus 0. Derivative of 1 is just 0, equals 0. Derivative of 0 is just 0. And now solving for dy dx. We see that dy dx, not dy dx, is going to be 1 over 2y. Oh, that's very interesting. Did I make a mistake somewhere? 2y dy dx minus 1 plus 0. Yeah, no, that's correct. So you see the x coordinates don't even matter. It's just the y coordinates. The y coordinates are the only thing that are going to change the slope, right? Because this is the slope of the tangent line. Anyway, so dy dx evaluated at the point to negative 1 is going to be 1 over 2 times negative 1, right? I'm just plugging in y. I'm plugging in y there. So that's negative 1/2. And then dy dx evaluated at 2 positive 1 is going to be 1 over 2 times 1, which is positive 1/2. Okay, and that's that one. It would have been more interesting if this was an x squared, maybe. Because then at least x plays a role in what the slope is. If I change this, so you don't have to write this down, but just watch. Like if I change this to an x squared, Now this makes the derivative down here 2x instead of 1, which would make this 2x, which would make this 2x, which would really mean x over y. And so then when I went to find derivative evaluated at 2, negative 1, well, I would plug in I would plug in 2 for x and negative 1 for y and get negative 2, right? And here I would get 2 over positive 1, which is positive 2. Anyway, so that's that one. Let me give you one last example for this section. And I'm going to go back to one of the examples that I gave you at the beginning of the lecture of something that was possible to solve for y, but not desirable to solve for y. And that was this equation here, x cubed plus y cubed equals 3xy. And this is called the Folium of Descartes. Descartes. Okay, René Descartes was a famous mathematician, philosopher guy. Anyway, and it would be you can graph these things in Desmos. It might be interesting for you to do that. It's kind of a cool looking curve. It's got like a little twist in the middle of it, which is kind of fun. But anyway, let's find dy dx for the Folium of Descartes. Okay, here we go. So differentiating this function here, we're going to have 3x squared plus 3y squared dy dx equals derivative of the first times the second plus the first times the derivative of the second. Okay? And then we solve for dy dx. So I'm going to move everything that has a dy dx on it on the left and everything else over to the right. So I'm going to have 3y squared dy dx minus dy dx, 1 times dy dx, right, equals 3y plus 3, oh, I'm sorry, no, it's a 3x times dy dx over here, isn't it? My apologies. This should be a minus 3x times dy dx. And then this equals 3y, and then I'm going to say minus 3x squared. Goodness, there are a lot of 3's. In fact, every single term has a 3 on it. I'm just going to go ahead and cancel those. So I've got dy dx times y squared minus x equals y minus x squared. That's very interesting. And then we divide through to solve for dy dx. So we get y minus x squared over y squared minus x. There you go. So there's the derivative of the Folium of Descartes. Now, let's find an equation for the tangent line to the folium at the point 3/2, 3/2. Let me silence my phone. Okay. So finding an equation for the tangent line to the folium at this point, 3/2, 3/2. Well, first of all, the slope of the tangent line is going to be this derivative evaluated at this point, right? So let's find that first, right? So the slope is going to be dy dx evaluated at 3/2, 3/2. So that's going to be 3 halves minus 3 halves squared over 3 halves squared minus 3 halves. Ooh, that's just -1, isn't it? I mean, it's like the numerator and denominator are identical, except that the order of subtraction has been switched around. So, I mean, if you wanted to justify it in just one more step, you could say this is negative 3 halves squared minus 3 halves, right? Over 3 halves squared minus 3 halves. And those things just cancel, right? This is just -1. So rather than going through all the work of like squaring the fractions and finding common denominators and stuff. Anyway, so the slope of the tangent line is -1. Now what's the equation of the tangent line? Well, we're going to say y minus y1. Okay, we're using this point. This point is on the curve. So y minus y1 equals m times x minus x1. In other words, y minus 3 halves equals -x plus 3 halves. Now add 3 halves over to the other side. Y equals -x plus 6 halves. That's the same thing as 3. So simple, right? There's the equation for the tangent line, -x plus 3. Okay. And we can answer one more question. We can say part C. At what points, or just point, right, if any, is the tangent line to the folium horizontal? Okay. Well, certainly not at 3 halves, 3 halves, right? That wasn't a horizontal line at all. So we know that it's not horizontal at 3 halves, 3 halves. But to figure out where it would be horizontal, we need to set the derivative equal to 0, right? Because the slope of a horizontal line is 0. And so we need to set this thing equal to 0 and then solve. I'm going to say y minus x squared over x squared minus y needs to equal 0. Okay. Well, if we multiply by x squared minus y, we get y minus x squared equals 0. So really, it's going to happen whenever y equals x squared. That's kind of interesting. So y equals x squared is when you get zeros. I guess to solve that for x, we should plug that back into the original equation. X cubed plus y cubed equals 3xy. So x cubed plus y cubed equals 3xy. Now if we're saying the only places where this thing is 0 is whenever y equals x squared, well, we should plug that into this equation, right? We should say it's going to happen whenever x cubed plus y cubed, y is the same thing as x squared, equals 3xy. So let's see if we can solve this equation now. So x cubed plus x to the 6th equals 3x cubed. Oh, that's not bad at all. Let's subtract 3x cubed. We'll have x to the 6th minus 2x cubed equals 0. And we can factor out an x cubed. And what solutions do we get? You actually get 3 solutions. So you would get this, right? You would get x cubed equals 0 or x cubed equals 2. And both of those equations are going to yield 3 unique solutions. So you get 6 solutions in total. However, 2 of the solutions that come from this equation are going to be non-real, and 2 of the solutions that come from this equation are going to be non-real. The only real solutions you get are x equals cube root of 0, right, which is 0, or x equals cube root of 2, which is, well, cube root of 2. 2 to the 1/3 if you like. But anyway, those are the two solutions, x equals 0, x equals cube root of 2. Now we were asked at what points is the tangent line horizontal. So for x equals 0, we need to now solve for y. So for x equals 0, we get, again, I'm using x cubed plus y cubed equals 3xy. So for x equals 0, we get 0 plus y cubed equals 3 times 0 times y. So in other words, y cubed equals 0, or in other words, y equals 0. So there's one point, right? So the point 0, 0 is one point on the folium where you get a horizontal line. The other point for x equals cube root of 2, we get x cubed plus y cubed equals 3x y. So 2 plus y cubed equals 3 times the cube root of 2 times y. Oh, that's so horrible that we have to solve this. We have to solve this for y now. Well, we've got y cubed minus 3 times the cube root of 2y plus 2 equals 0. Goodness gracious. How do we do that? Well, how do we do that? Well, okay, so the trouble is, this is a cubic. I wonder if it's factorable. I kind of don't feel like it is. You know what? I'm gonna stop recording and figure this out, and then I'll come back and tell you the answer.